The next speaker is Jayant Thatte. Jayant is a PhD student at Stanford working with Professor Bernd Giraud, and today he's going to be talking about a perceptual evaluation of 6th degree of freedom virtual reality rendering from stacked OmniStereo representations.
Okay, hello everyone. My name is Jayant Thatte. I'm a PhD student at Stanford, and I'm advised by Professor Bernd Giraud. Today I'll be talking about some of our ongoing work regarding motion parallax in VR, so very much an extension to the talk that Harry just gave. My talk will be structured as follows. First, I'll talk about a subjective study that we conducted to see how important motion parallax is. And then once I convince you of the importance of motion parallax, then the next thing is we would like to understand how much people move typically if they are seated in a chair and viewing something in VR. So we recorded some head trajectories and created a distribution of people's motion. And finally, I would like to talk about the rendering system that we developed that can respond to the viewer's head movements in real time. Okay. Again, Harry briefly talked about this, but there are two different types of VR content broadly. There's cinematic VR and there's synthetic VR. And in cinematic VR, we would start with a natural scene, a natural environment, and use some sort of a camera system, and then capture and process the data to finally show it on a head-mounted display. As opposed to this, in a synthetic environment, we would start with a 3D model of the scene, and then use something like Unity to render an appropriate viewport in the display. And the key difference between these two is that in synthetic VR, we have a full 3D model of the scene already available to us. Whereas in cinematic VR, the data that we have is in some sense a lot less rich, and there's a limit on how much we can capture and store. And this means that supporting 6 DOF or motion parallax in synthetic VR is relatively a lot more straightforward than for cinematic VR. And so we would like to develop algorithms that will work for cinematic applications. Okay. Now, with that background, I'll talk about the subjective study. Like I mentioned, the goal of the subjective study is to understand the importance of 1, motion parallax, and 2, binocular disparity when it comes to the perceived quality of experience in VR. And to do this, we tested 6 different VR settings. So as you can see, there's mono and stereo. And we combined this with 3 different parallax settings. So the first setting is just no parallax, which is how things are conventionally rendered for immersive video. Then we have only horizontal parallax, where the viewers can move left and right and back and forth, but there's no up and down motion. And finally, full parallax or 6 DOF, where the viewer is not really constrained and they can do whatever they want. This is a snapshot of the test scene that we used. So it's a simple toy scene that we created just for this subjective study. And it just consists of a bunch of different cubes floating around in space. The closest cube was 1 meter from the viewer. And the starry background that you see is located at infinity. Okay. The test format, we showed viewers with 30 pairs of stimuli, where each stimulus corresponds to one of those 6 VR settings I mentioned earlier. And they were asked to, for each pair of stimuli, they were asked to rate the second stimulus relative to the first one on a 7-point scale. So -3 means that the second setting was much more preferred than the first, the other way around. So -3 is the second setting was much worse, and +3 is much better, and sort of uniformly in between. We also recorded the 6 DOF pose of the head-mounted display. This can be done natively using the Oculus Rift positional tracker. And we use this later to create the distribution. I'll talk about that later. And we had 17 participants in our subjective study. Okay. This chart summarizes the key finding of the subjective study. The y-axis indicates the mean opinion score. So positive is better, but means that setting was more preferred, it was more comfortable. And the different bars that you see correspond to the 6 different VR settings. So you have no parallax here, and then the 2 middle bars are for only horizontal parallax, and then you have full parallax on the right. And in each case, the left bar is for monoscopic vision and the right bar is for stereo. Okay, now let's start making some observations. The first thing that we notice is that motion parallax seems to be really important. So if you start from a system that is monoscopic with no parallax, the biggest gain that you can get is by just adding horizontal parallax, and you're already doing much better. And again, if you add also vertical parallax, you get a lot more improvement still. The second thing that we notice is when we are rendering something with 6DoF, stereo seems to be a lot more preferred than monoscopic rendering. However, if the parallax that is rendered is either limited or if there's no parallax, then rendering the scene in stereo doesn't really give you any benefit. And so this means that if you're starting from a monoscopic, no parallax system, your first goal should be to figure out how to get parallax in your system rather than getting stereo. Okay, now that I've tried to convince you about how important motion parallax is, the next goal is to get an estimate of how much people tend to move when they are viewing something. And again, all of this is for a sedentary observer. So all the 17 participants were requested to be seated in their chair during the experience. And the two graphs that I'm showing you are the distribution of their movements. So the graph on the left shows the horizontal motion, and the graph on the right is the vertical motion. And we noticed that 90% of the horizontal motion falls within a circle of radius 30 centimeters. So the viewers are inside of that circle horizontally when they're moving. And similarly, 90% of the vertical motion falls within plus minus 8.5 centimeters. And so these numbers would be important for designers or engineers who are planning to implement systems that are showing immersive video to sedentary viewers, because that's sort of the range of motion that you should design for. Okay, now since I've talked a lot about motion parallax, in the last part of my talk, let me move on to actually giving you the details of the real-time system that we implemented that can render views with 6DoF within a limited viewing volume. And to do that, like Robert did, I'm going to start with OmniStereo, and I'm actually going to borrow his slide because it's a very well-made slide. So you can think of OmniStereo as being captured by a pair of rotating cameras, and in each direction, each camera captures a narrow vertical slit, and all of these slits are then mosaicked together to give you a left and a right image. And this is the conventional format that's widely used in YouTube and all kinds of VR platforms. Okay, so Stacked OmniStereo is a VR representation that can render motion parallax. And it starts with OmniStereo and modifies it in a couple of key ways, in a few key ways. So let's start with OmniStereo. We are all familiar with this by now. It's a pair of rotating cameras. The distance between the cameras is the same as the distance between our eyes. And that gives us a left and a right panorama. Now, the first thing that we do is we also add depth to it. So now, in addition to having two texture panoramas, we also have the two corresponding depth panoramas. The next thing that we do is we expand the stereo baseline. So now the diameter of this circle is much larger, and the goal here is to make this circle large enough so that most of the viewer's head motion falls inside of that circle. And finally, we stack two of these on top of each other, and that will give you this sort of a cylindrical viewing volume. And anywhere inside of this volume, novel views can be synthesized with high quality and usually without inpainting. And the representation itself looks like this. You have 4 texture panoramas and the corresponding 4 depth panoramas. Of course, in practice, we would likely implement this with 2 camera rigs on top of each other. And a description on how a representation like this can be constructed from camera rigs can be found in the original paper from last year. Okay, and for the rendering system, we use a diameter of 40 centimeters and a height of 20 centimeters. Now that I've explained what the representation is, in the second part, I'm going to talk about how actually one would render novel views from this representation. And this happens in 2 parts. The first part is hypothesis generation, and this happens once per panorama. So we start with any one out of the 4 OmniStereo panoramas, the SOS panoramas. And remember that each stacked OmniStereo panorama has a depth component and a texture component. We start with the depth component, and knowing the depth at each pixel, we can project all of these points onto the target viewport. And that would give us something like this, where pixels land at sort of arbitrary locations. And then we run a depth interpolation, and that gives us the final target depth map. Now, knowing the depth value at each pixel in the target depth map, we repeat these calculations in the reverse direction. And for each pixel in the target depth map, we try to find the location in the texture panorama, which would map to that pixel. And then from the texture panorama, we copy over the RGB value after bicubic interpolation, and that would give us this final view. Now remember that this is only one of the hypotheses for what the final view should look like. And since we have 4 different stacked OmniStereo panoramas, we would get 4 such hypotheses. So that's shown over here. So that's your representation on the left. And you get 1, 2, 3, 4 different hypotheses. And now notice that the black regions that you see, which are the disocclusion holes, they are by design on different sides of a foreground object. And so if we just combine all of these, even without using in-painting, we end up with a view that looks something like this, where the holes already get filled because they're non-overlapping. And additionally, since we have 4 different hypotheses of each region in the scene, by combining them in the appropriate with the appropriate weights, we can also approximate some view-dependent specular highlights. Okay. Implementation details. The whole system runs on a 6 GB NVIDIA GPU. Everything is displayed on Oculus Rift headset. Currently we're able to get 45 frames per second, but there's some more room for optimization still. And the resolution is it's stereo rendering at 1344 by 1600, which is the recommended resolution for Oculus Rift headset. Okay, so here is one of the results. So this is one viewpoint, and this is a second viewpoint. And you can notice the parallax between the white coffee mug and the carrots placed next to it. Now remember that both of these views are still within the cylindrical viewing volume that I talked about earlier. Here is a similar example for the Facebook scene. So this scene is one of the open source scenes available through Facebook's Around 360. And you can, for example, notice the parallax between the chair and the tree, and between the foreground tree and the background tree when I toggle back and forth. And here is another example, just 2 different viewpoints. Okay. And now the last thing that I would like to do is show you 2 different videos. One video shows the experience of the viewer without motion parallax, and the second video shows the experience with motion parallax, and hopefully you'll be able to appreciate that motion parallax makes a big difference. So this is me just trying to view something in VR. And the motion parallax is off right now, so you'll notice that the view only turns. But if I move closer or farther to something or move side to side, the view doesn't really change. So here I'm trying to move closer, but nothing changes in the output view. Whereas with motion parallax, you can interact with the VR environment a lot more naturally. You can move closer, you can look around objects, you can look under objects. And of course, the red pixels that you see are the pixels where data wasn't available from any of the 4 source panoramas. This would either happen in more complex geometry, where it just happens that a region is disoccluded from all 4 source views, but somehow becomes visible in the target view. Or it can happen when the viewer moves outside of the cylindrical volume, and then we need to sort of fill in those pixels using in-painting. And that's what happened over there. I moved too much and went outside of the viewing cylinder. Okay, so with that to conclude, I I first started by talking about a subjective study, and we found through the study that motion parallax is probably more important than rendering stereo if you want to provide viewers with a good VR experience. Secondly, stereo rendering is really important if you're also rendering motion parallax. If your system doesn't support motion parallax, then we found that stereo and monoscopic renderings perform almost similar to each other. Thirdly, 90% of the horizontal head motion for a sedentary viewer is within 30 centimeters, and the vertical motion is within plus minus 8.5. And of course, the results of the subjective study and the distribution that I'm showing is of course scene dependent. So we tested one specific scene, and I would expect that the trend would be similar, but the actual numbers might vary a little bit if we used a different scene, and that would be an interesting thing to explore. And finally, we demonstrate a proof of concept VR rendering system that can render on a single GPU and still provide 6 degrees of freedom experience within a limited viewing volume. With that, I'm going to stop, and I'm going to just leave this one final video running where you can. I don't know if it's easy to see on the projector, but you can see the specular highlights changing on the monkey as the viewpoint changes. And by the way, thanks to Trisha for rendering the synthetic scenes for this. She's going to give an amazing talk right after me. But yeah, with that, I'm going to stop and take questions.